Today let's discuss about the basic S and curve. You see the basic form of S and curve used for a design is expressed mathematically like a log n equal log k1 minus m into log s. Usually this comes like n equal to a into s power minus m. That's a relationship that we can convert into the logarithmic equation. Okay, so if you see here, n is nothing but the predicted number of cycles to failure. This is the number of load cycles the material can withstand before it fails under a given stress amplitude. So for this stress amplitude, how much number of cycle the material can withstand, that can be predicted by this n number. Like, so this is the predicted number of cycles before failure. That much the material can withstand, especially for this given stress range. So S is the stress range. That's the difference between the maximum and minimum stress and the material experience. In a cyclic loading, there could be a maximum tension stress, maximum compressive stress. This difference between these two, that gives the range during the cyclic loading. So this is the stress maximum and minimum the material experiences during each loading cycle. A1, the K1 is there, right? That's a constant which depends on the material type and joint type. So it depends on only the material type and joint type. Material and joint type. M is the inverse slope of the ascent curve, which varies depending on the type of material loading conditions. This value determines how steeply the curve declines as the stress range increases. You can see this ascent curve, it can go like this. Here M equal to 3 slope. Here M equal to 3. And this will be a little bit flat, m equal to 5. This is the vertical axis and this is horizontal axis. Horizontal axis n, vertical axis is s. So this curve, this m, that determines like how steeply the curve declines. This is decline, right? Declines as the stress range increases. Okay, the mathematical physical explanation, if you see the equation logarithmically relates number of cycles applied to applied stress range. So what it happens, this equation, it logarithmically relates the number of cycles to failure to the stress range. So there is a relation between the number of cycle and stress range. That relation we are logarithmically relating. That's the equation we are getting. M, the parameter m is critical because it dictates fatigue strength of material. For materials with low fatigue strength, this value will be relatively large. The curve steeply drops, meaning the material fails more quickly under the high stress. If the stress is increasing, the number of cycles to failure also it's getting reduced. You see the stress from this point, stress is less. If this point, stress is more. If the stress is increasing, that means the number of cycle also it's coming down. For this low stress, you have high number of cycles it can withstand before failure. If it is very high stress, it has very less number of cycles to withstand before failure. That's why this m is important. This m dictates like how the material fails more quickly under the high stress. And then there is a constant like value k1 is related to the material's intrinsic properties and type of joint. For different materials, well, that cast it as different values. And there is one more point, is the thickness effect. For welded joints, the basic SN curves is based on the reference thickness. Whenever we are developing the SN curve, they are using the reference thickness. That reference thickness is 16 mm. That's how this basic SN curve was developed. So when the material thickness is greater than the reference thickness, suppose if you are checking for the 30 thick plate, 30 thick tubular member, where the thickness is more than this reference thickness 16, so we need to apply the thickness correction factor to account for the change in fatigue life. So something called thickness correction factor we need to apply, and then this correction is represented by the formula S equal to S naught into T ref by T whole power 0.5. Here S naught is the allowable stress range based on the basic SN curve. This S naught is nothing but basic SN curve, that's based on the reference thickness. And T ref is the actual thickness. T reference is the reference thickness, that's 16 mm for welded joint and 38 mm for cast joints. T is the actual thickness of the thickness at which the vertical life is being predicted. So mathematical physical explanation, if you see the formula accounts for the thickness effect of fatigue life. In essence, the thicker materials can handle higher stress range before failure as they have more material to distribute the load. Therefore, the allowable stress range is adjusted based on the ratio of the reference thickness to actual thickness. The exponents 0.25 or 0.15 for casting reflects the empirical relation between the material thickness and fatigue strength. The empirical relation was derived based on the experimental data Based for the common materials like steel, it shows the thickness increases, the fatigue life improves, but at a diminishing rate. Thickness effect for cast joints, the value is changing to 0.15. And if you see the effects of seawater, for welded joints exposed to seawater, especially those with cathodic protection, and curve needs to be adjusted for the impact of seawater environment. So effects of seawater also needs to be accounted for in this SN curve. Yes, seawater can significantly accelerate corrosion, which can reduce the fatigue life of welded joints. So whenever it's getting exposed to seawater, it will accelerate the corrosion, right? So it can reduce the fatigue life significantly. So to account for this, the M equal to 3 that branch of SN curve is reduced by a factor of 2 on life, and the M equal to 5 branch remains unchanged. So there are two branches, M equal to 3 and M equal to 5. In this one, M equal to 3, this branch is getting affected by the effect of seawater. That how we are taking means by reducing the factor by SN curve is reduced a factor of 2 on life. Seawater exposure leads to corrosion that can weaken the materials, reduce the resistance to fatigue failure. By reducing the predicted fatigue life for welded joints in seawater, this adjustment accounts for corrosive environment that accelerates material degradation. The factor 2.0 means the material's predicted number of cycles to failure is halved under seawater conditions with cathodic protection. This empirical relation correction to ensure the durability of welded structures exposed to harsh marine environments. And let's see some discussion with designers like engineers. Alright everyone, let's talk about the SN curves we are using for tubular joints. I was reviewing the data and I have got a couple of questions. First, we are using these curves for welded joints as well as cast joints, right? Can someone explain the key difference between how we apply them to welded joints versus cast joints? Yes, that's right. For welded joints we use WJ curve. For cast joints we use CJ curve. There are two things, WJ curve and CJ curve. The main thing is that to note is that for welded joints the curve is based on the assumption that we are working with steels having yield stress under 500 MPa. But for cast joints we have a different approach and different constant to account for the material properties of castings. Interesting. So you mentioned that we use the curves of materials with yield strengths under 500 MPa, but what if the material is exposed to seawater? Does that change things? Suppose yes, we have seen like if it is exposed to seawater, that's going to change. That's the question, like does that change things? Yes, it does. For welded joints in seawater with cathode protection, we have to reduce the life prediction by a factor of 2 for M equal to 3 branch. For M equal to 5 stays unchanged, but we need to adjust the slope change position accordingly. Wait a second, are we also considering the corrosion protection when we are dealing with cast joints exposed to seawater? Because I read somewhere that if there is a not adequate corrosion protection, SN curve changes. That's right. That's actually a section that explains if provides plots of WJ curves versus data in seawater. We have to be cautious. This just highlights how important the environmental factors are. So it's clear that we have to adjust the SN curves based on the environmental conditions. But what about the material thickness? I was going through a section. Seems like thickness effect is important too. How does that work exactly? WG curve seems 16 mm is a reference thickness. If the material thickness exceeds this, we need to apply correction factor. For example, the allowable stress gets adjusted using the formula. So if the welded joint has a profile control, we can change the exponent in that equation, right? What happens if the welded toe is ground or pinned? If the weld has profile control, the exponent changes to 0.2. If the weld toe has been ground or pinned, the exponent changes to 0.15. So this exponent we are talking about, this exponent can go to 0.2 or 0.15 depending upon how much it's treated. Like the weld profile control means we can use 0.2. If the weld has to be ground or pinned, then the exponent drops to 0.15. That's a significant improvement in the fatigue life prediction. So that would cause a significant improvement in the fatigue life prediction. So got it. But what if you're working with cast joints? Does this thickness affect the change for castings? Yes. Cast joints also we are using reference thickness. And what happens if the material thickness is less than the reference thickness? Say the thinner for a joint. If the material thickness is less than the reference thickness, no effect is applied. We only use the correction factor for material thickness that exceeds the reference thickness. Also, what thickness would be used for the hotspot in the joints? Chord connection. Hotspots, chord joint contributors, we use the chord thickness in the equation. For the brace side, we use the brace thickness. That's important to remember when calculating the fatigue life of based on the location of the hotspot. This really clarifies how to approach the design for tubular connections. So to wrap things up, we need to consider the SN curves, environmental conditions, material thickness, location of hotspots to ensure accurate fatigue life predictions. Thanks for your input. Everyone, it's always great to dig into these details to ensure we are applying the right method and formulas in our design. Alright, let's dive into this. We are here to discuss Sn curves for the tubular connections, especially the welded joints, and looking for the equations. Honestly, it's fascinating how these curves help predict the failure cycles under stress. Let us check how the basis works. Okay, let me read through this. Equation is this one. It seems like we are trying to predict the number of cycles to failure based on the stress range. So what are we doing? Like, we are trying to predict the number of cycles to failure for the based on the stress range applied to the material. The constant K1 plays a big role. Yes, the constant K1 is crucial because it depends on the material type and its properties. For welded joint, we have to use K1 based on the typical material strengths. I see that M is the inverse slope of this curve. Hold on. How exactly does the value of M change for different stress ranges? For n equal less than 10 power 7. 10 power 7, M is 3. For welded joint, n is greater than 10 power 7. It switches to 5. Its n is greater than power. What's the significance of that change? Great question. Pulling up a diagram. This is what I find really interesting. When n is smaller, we are dealing with higher stress. When n is smaller, we are dealing with higher stress. The material tends to fail faster. When n is smaller, we are dealing with high stress. Material tends to fail faster. So we use a steeper slope. M is 3 is a steeper slope because it's a steeply slope, and M is 5 is a little bit flat slope, less steep. But when n is larger, number of cycles more, we are dealing with the lower stress and the more cycles. The slope becomes less steep, indicating the material can withstand more number of cycles before failure. So when we are dealing with high number of cycles, low stress, we are using the slope of m equal to 5. When we are dealing with less number of cycles and high stress ranges, we are using m equal to 3. M equal to 3 is a more steep one, and m equal to 5 is less steep one. So what I am gathering that for welded joints, when you are predicting the failure over a small number of cycles, you are using a steeper curve because material gets fatigued quicker. When the number of cycles increases, the slope flattens because the fatigue will happen more gradually. As we can see that for welded joints, K1 values are given in, and assume that it's a unit conversion but underlying. So absolutely, the next thing we need to consider is thickness effect. I see the SN curve forwarded for welded joints is based on the reference thickness of 16, but for thicker we can apply correction factor. That's why the thickness effect is formula we are giving it. Yes, that's the equation. The thickness effect is essentially just the allowable stress range, yes, based on the actual thickness and the material compared to the reference thickness. For welded joint, if the material thickness is thicker than 16, x1 0.25 is used to adjust the stress range. It makes sense when you think about it. The thicker materials will generally resist fatigue failure better. And but wait, there's a catch. If the weld has a profile control, the x1 changes to 0.2. If the weld has been ground or pinned, it changes to 0.15. Why these adjustments? Shouldn't the original experiment still apply? It's a good point. The reasoning is that profile control grinding pinning improves the material's resistance to stress concentration. Essentially, these treatments improve the weld's performance, allowing for better fatigue life. So we are tweaking the experiment to reflect that improvement. I think I'm following now. Like, so for cast joints, we have a different thickness effect equation, right? Exponent is that is 0.15, reference thickness 38 mm. What's the crucial role here that the SN curves are used in different environments? For instance, seawater effects. We adjust the SN curve for welded joint exposed to seawater with cathode pressure. M equal to 3 branch gets reduced by a factor of 2, but M equal to 5 stays the same. How do you think this affects the design? The idea here is that the seawater with cathode depression can reduce the life of the welding joint, so we need to account for this in the design. But why only adjust M equal to 3 branch? Leave M equal to 5 unchanged. I think it's because M equal to 3 branch corresponds to high stress, low fatigue, low cycle fatigue. M equal to 5 is low stress and high cycle fatigue. In seawater, the high stress cycles are more significantly impacted, but the low stress cycles are less impacted by corrosion. So the real